In this video, we'll be talking about unbanked curves. So we have a question here. It says a sports car travels at a constant speed of 7.5 meters per second around an unbanked curve that has a radius of 25 meters. What is the coefficient of static friction of the car's tires to the road? Before we actually address the question, it is important to draw it out. And so what you're seeing is two diagrams. The first one is looking at a bird's eye view of the curve. So here's the curve. The curve has a radius. If you look at the curve, it almost looks like a circle, and any circle has a radius. And so here's the center of it, and here is where the car is at. So the radius is basically the distance the car is to the center of the curve. And so we said that the radius is 25 meters. Now, to the right, we have a diagram of the car itself, but we're looking at it at eye level at the rear of the car. So this is a rear eye or a rear view of the car at eye level. And the reason why I drew this out is because it is important to draw a free body diagram so we can kind of get an idea of the forces that are acting on it. And so first thing we're going to do is we're going to draw all the forces acting on this car. One of the first things that you notice is that the car has a weight, which goes down like this. And so we're going to label that as W for weight. You'll notice that the car is also experiencing a normal force, and we say that there is a normal force because the road itself is pushing up against this car. Right? And so the normal force actually goes in the complete opposite direction of the weight. So the normal force actually goes like this. And then we'll label this as F sub n, which represents normal force. Keep in mind that the normal force and the weight are equivalent to each other. And the reason why is because the weight and the normal force are along the direction, the vectors of the force normal and my weight are along the same axes. And so we can say that the force normal is equivalent to the weight, which is equivalent to mass times gravity. Keep that in mind. We're going to actually look at that in a little bit, just a bit later in this video. We're going to go ahead and talk about the other two forces acting on this car. One of the forces that is acting on this car going sideways is the applied force, which goes in this direction. Just like that. And if I were to look at the car here from a bird's eye view, the applied force goes like this. Okay. This is what we're seeing right here. Okay, so the applied force going towards the right, the applied force going towards the right. As you notice, the applied force is actually pointing away from the curve. It's actually the force that you feel that when you negotiate, when you go around a curve. When you go around a curve, you feel a shift going in the direction that you don't want to go. When you're swerving left, you feel a force going towards the right. And it almost feels like you're going to skid off or fall off the curve. That is known as the applied force. That's the force that you're feeling as you're going around the curve. So what happens if the car is right here at this point? And the car is actually going this way, just so you know. It's going like that. What happens if the car is right there? Well, your applied force is now directed this way. Just rewrite it so it goes in this direction. And if your car happens to be here now, oops. If your car is here, your applied force is going here, like that. Okay, so the applied force is the force that is directed away from the curve. It's the force that makes you feel like you're going to swerve off of the curve. There is another force that is acting on this car, and it's the force that goes in the opposite direction of the applied force. just like this. And this particular force is known as the frictional force. So the symbol for frictional force is capital F sub F, just like that. And it goes in the opposite direction of the applied force. Okay, so if I were to look at the bird's eye view again, you'll notice that the applied force goes, well, if I'm looking at this part, if I'm looking at this car, on this part of the diagram, the applied force goes outwards like this. The frictional force actually goes in the opposite direction, like that. Let me use a line actually, so let me just show this to you really quick. So the frictional force goes like that. If the car is at this point right here, you'll notice that the applied force goes up, the frictional force goes in the opposite direction of the applied force, so it goes down like this. And if the car is here with your applied force going this way, the frictional force goes in the opposite direction of that applied force, which goes like this. Okay, so all of that, those yellow arrows that you're seeing, is the frictional force. Okay? Why am I telling you this? Because the frictional force is pointing towards the center of the curve, or the center of the circle. It is said to have what we call a centripetal direction. Or in this case, we're going to call it centripetal force because we're dealing with frictional force. The word centripetal means center seeking. So anything that is pointing towards the center is considered centripetal. And this is for anything that spins, anything that goes around something, anything that's flung in a circle, like a sling and a rock. Planets orbiting the sun, they orbit in a circular fashion. Anything that goes around a circle has some sort of center-seeking force called the centripetal force. It's the prime force that keeps things going around and around and around. Without the centripetal force, objects can't safely go around and around and around. And so in this case, for this car, the friction is the one that keeps the car on this curve. It keeps the car, it's able to have this car negotiate the curve safely. It's able to go around the curve safely. And you notice that the frictional force is directed towards the center. So this means that the frictional force is equivalent to your centripetal force. So in unbanked curves, what you need to remember is that the frictional force is the center-seeking force. The frictional force is the centripetal force. Now, let's break this down really quickly. Frictional force has its own equation. If you were to look up the equation for frictional force, it's mu times force normal. Okay? For this particular question, we're actually going to replace force normal with weight because the force normal is equivalent to the weight. Force normal equals the weight. So I'm going to just replace the force normal with weight. So we can say mu times W, or you can just simply say mu times mass times gravity. Okay? That's the equation for frictional force. The centripetal force has its own equation, and so let's go ahead and look at that. If I were to look up the equation for centripetal force, it's mass times velocity squared divided by the radius. Okay? And so that's the equation for centripetal force. Now, if I were to take both of those equations and put them together, in this case, we're seeing that the centripetal force equals the frictional force. Let's go ahead and break down both of these guys to what they stand for. So I'm going to go ahead and break down frictional force to mu times mass times gravity. And I'm going to break down the centripetal force to mass times velocity squared divided by radius. And so what we just did, was we substituted the centripetal force and the frictional force for that. Now when you look at that, you'll notice that you can actually simplify it. You can look, if you look at the masses, what happens to them? They actually cancel out algebraically. And what we just did was we simplified the equation to this. Velocity squared divided by radius equals the coefficient of friction times gravity. And what you see here now is the primary equation that is to be used whenever you're dealing with unbanked curves. So this is the unbanked curve equation. This is something that you might need to know, okay? We're going to actually use this equation to solve for our question here. So the question again, what is the coefficient of static friction of the car's tires to the road? So let's break this down. The question is asking for the coefficient of static friction. So we're looking for mu. We know our velocity, which is 7.5 meters per second. That's basically how fast the car is going around the curve. And we also know how big that curve is. We know the radius of it. So our radius is 25 meters. Let's go ahead and take these values and plug it into our unbanked curve equation. So here we are. Before I plug in my values, it is important to make sure that the equation is set up so that way we have the unknown isolated by himself. It's not by himself right now. You'll notice that gravity is right there with it. So let's go ahead and move gravity to the other side so that way we can get the mu by itself. So I'm going to divide both sides by gravity. That cancels out, and now our equation is velocity squared divided by r times g equals mu. And now we are ready to solve. We have the radius, we have the velocity, which is 7.5 meters per second. So I'm just going to write that up here. And don't forget to square it because the equation says square it. And on the bottom we have the radius, which is 25 times our gravity, which is 9.80. Once you have your values plugged in, let's go ahead and solve it. Okay, so 7.5 to the second power divided by 25 times 9.80 gives us a total of 0.22959. It just keeps going. I'm going to round this to two significant figures, so our answer is rounded up to 0.23. And that is our mu. Keep in mind that our mu, our coefficient of friction, is a dimensionless value. Okay, it's just a number. That's all it is. And so what we just did was we solved our coefficient of static friction. One thing to note here, if the question is simply just asking, instead of asking, let's say instead of asking for coefficient of static friction, let's say if the question says what is the frictional force in general. If the question is just looking for frictional force, just keep in mind that the frictional force is equivalent to the centripetal force. And you only need to break down the centripetal force, and you can just leave the frictional force as is. So I'm going to write it over here. Okay, so centripetal force equals the frictional force. And if the question is asking for frictional force, then all we know is the velocity and the radius, which is that. All you need to do is just break down the centripetal force to this, which is mv squared divided by r, and you can just say that is the frictional force, and then you can just plug in your values and solve it.